Alright, dear children, now we are moving to the numerical problems, important numerical problem that we solve now from this chapter, matter wave. Okay, there are very few numericals that we solve and try to understand. Okay, so let's start with problem number 1. The problem number 1 says that electrons, as one of the matter particle, initially at rest. Initially at rest means what? Velocity 0. Initial velocity 0. Okay, so let me just consider u is 0. Because u is the initial velocity which is 0, are passed through a potential difference. Means this electron are passed through a potential difference of 2 kb means kilovolt. So potential difference B is 2 kb means kilovolt. But I convert this kilovolt into volt. So kilo means, you know, what is the order? 1000. So 2 kilovolt equals to 2000 volt. 2000 what? Volt. Okay. So what actually we need to calculate in this problem? Calculate their first part de Broglie wavelength. So we need to find lambda. Okay, then after we calculate the final velocity, means B also we need to calculate. So that means this question has two subparts that we need to calculate. Okay, but in the question the value of H is given. See what is the value of H? 6.6 into minus 34 joule second. Me out here implies the mass of the electron, 9.1 into minus 31 kg. Now to calculate the first part, de Broglie wavelength, when the potential difference is given directly, so we use the formula, and the formula is de Broglie wavelength, and de Broglie wavelength, okay, of electron is given by lambda equals to 12.27 by square root of B, and this will measure directly in Armstrong. So children, in the last YouTube video only you learned this relation, we derived this relation. Means de Broglie wavelength can be measured directly in terms of potential difference. So let me just substitute the value now. This is 12.27 whole divided by square root of B means how much? 2000, and we measure in Armstrong. Now we can take the square root of 2000. But 2000 is not a perfect square. Okay, so if you use square root and calculate the square root of 2000, it comes approximately 44.72. So I am writing in two decimal places. 44.72. Now 12.27, if I divide by 44.72, we get approximately, with the help of calculator, 0.2744. Okay, let me write in 4 decimal places, no problem. Because these wavelengths are very small, so I can write the answer in 4 decimal places also. So what is the de Broglie wavelength of the electron? 0.2744 Armstrong. So this is the de Broglie wavelength. So the first part of the question is solved. Now the second part of the question, where we need to find the final velocity. We need to calculate final velocity. Now in order to calculate final velocity, again I use the formula de Broglie wavelength, but with this formula. Lambda equals to H by mb. Yes, this is a general formula that measures the de Broglie wavelength for any of the particle, but we are dealing with electron. But so that I write out here is me. So children, no confusion out here. This me means the mass of the electron. Means we are actually dealing out here with electron. So de Broglie wavelength we have calculated. H is known. Okay, mass of the electron is known. So B we can calculate. So I'll make B as the subject. It will be H by me into what? Lambda. Okay, H, Planck's constant value 6.6 into 10 minus 34 whole divided by me, the mass of the electron, how much? 9.1 into 10 minus 31 into lambda. Lambda means 0.2744, and this is the de Broglie wavelength into 10 to the power what? Minus 10 meter. Because I have to convert this Armstrong into meter. That's why to convert Armstrong into meter, I have to multiply by 10 to the minus 10. Okay. Now let me just do the calculation of this part. Okay. Now minus 34. Now this power I'll take in the numerator. So 6.6 by 9.1 into 0.2744 into the minus 34. 10 to the minus 34. The minus 31 plus minus 10 means minus 41. So it and minus 41, if I take in the numerator, is plus 41. So children, I have done directly out here. This 2 power will be added, and if I take in the numerator, it will be the minus 41 become plus 41. So it will be 10 to the power minus 34 plus 41. So children, this can be done, calculated. Now 41 minus 34 means 10 to the power 7. Power is 7. Okay. Now 6.6 into 10 to the power 7 divided by 9.1 into 0.2744. Now we can further simplify. In the numerator it is 6.6 into 10 to the power 7 by the denominator. As you know, in the last step you saw is 9.1 into 0.2744. Now if you multiply that quantity in the denominator, you get approximately 2.4970. So the calculation of that 9.1 into 0.2744 give you 2.4970. Now these two quantity again can be divided. So if you divide, we write as 2.643. So children, you can divide and calculate the value, and your value of de Broglie final velocity of the electron will be how much? It will be 2.643 into 10 to the power 7, and the unit is meter per second. So what is the answer? 2.643 into 10 to the power 7 meter per second. So this is the velocity of the electron. What velocity? Final velocity. So children, I have done one problem based on de Broglie wavelength. This is problem number 1. Now we even solve problem number 2 also. And problem number 2 says that calculate de Broglie wavelength. Again we have to calculate de Broglie wavelength of an electron only. We do with electron only. Of energy means this is the kinetic energy, which is 400 electron volt. Means your kinetic energy K is given in electron volt, which is 400. EB means electron volt. Because children, you know that energy can also be measured by the smallest unit, electron volt. But to calculate de Broglie wavelength, so I convert first this electron volt into joule. And there is a relation, children. 1 electron volt means 1.6 into minus 19 joule. So to convert electron volt to joule, so what we need to do? You have to multiply by 1.6 into minus 19 joule. So if you do multiply, 4 into 1.6 means 6.4 into 10 power. Now this 20 means 10 power 2. 2 minus 19 means minus 17 with joule. So K equals to 6.4 into minus 17 joule. Now next, in this question, electron is expressed, but the electron mass is not given. But children, you know mass of the electron is always 9.1 into minus 31 kg. So electron mass we always take as 9.1 into minus 31 kg. Okay. Now from this mass and this kinetic energy, we can calculate the de Broglie wavelength, and there is a formula. De Broglie wavelength lambda equals to h by square root of 2 mk. So in terms of kinetic energy, we can use this formula. See, lambda equals to h by square root of 2 mk, where this m is the mass of the electron. Okay. So let's substitute the value. Now in this problem, h, the Planck's constant, we take approximately same 6.6 into minus 34. The value of Planck's constant we take 6.6 into minus 34. Square root of 2 mass of the electron, 9.1 into minus 31. Kinetic energy, which is 6.4 into 10 minus how much? 17, minus 17. Okay. Now we can simplify this. So in order to simplify this quantity, now let me write this same numerators, 6.6 into minus 34. Let me first simplify the quantity inside the square root. 2 into 9.1 into 6.4. If you do multiply, we get approximately how much? 116.48. If you multiply 2 into 9.1 into 6.4 with the help of calculator, you get approximately 116.48 into 10 to the power now minus 31 power exponent and minus 17. This power will be added. If you add this power, it will be minus 48. Minus what? 48. So 10 to the power minus 31 and 10 minus 17 means 10 to the power minus 48. Okay. Now this power inside the square root is an even number, even power. So we can take the square root now. So we'll take the square root of this quantity. So 6.6 into 10 minus 34 whole divided by, now take the square root of 116.48 with a calculator, get approximately 10.793. so I am writing directly 10.793 into square root of 10 minus 48 means minus 24. The half of 48 means 24. Now this power I'll take in the numerator, and at the same time I'll divide 6.6 by 10.793. Okay, so divide this two quantity, children. You get 0.612. You get approximately 0.612 into 10 power minus 34, and if I take numerator minus 24, it becomes plus 24. Minus 34 plus 24. I mean, these two subtraction means minus 10. So I write down 0.612 into 10 power minus 10, and this is actually we are measuring wavelength in meter. But as I said, children, this wavelength can be measured in Armstrong also. So this 10 power minus 10 meter can be replaced by 1 Armstrong also. Okay. So your lambda de Broglie wavelength can be written as 0.612, and the unit I write down as Armstrong. So look at the value of de Broglie wavelength. So that is 0.613 Armstrong. So this is the solution of problem number 2. Now children, we have 2 more numerical problem to solve, okay, and that we do in the next YouTube video.